Good afternoon, everyone. I hope you can all hear me. And I'd like to welcome you all here in the Noodoption team, and especially everyone from the EAGE. Welcome to Fugro here. And my name is Elina. I work here in Fugro Innovations, and I'm also part of the board of the EAGE. And today we have an event, a live event, that is a collaboration between Fugro and the EAGE. And we have two tech talks today for you, where we're going to tell you about the variety of innovations where Fugro is involved in. And we also go a little bit more in depth into several of these innovations, where we tell a little bit more about the near-surface characterization of offshore wind farms. And before I give the floor to Diego, I would like to do a little safety moment before we start. In the case of a slow move, please leave the building immediately through that door over there, or through the door where you came in by the reception, and then we all gather around in front of the garage. Thank you again for coming, and now I want to give the floor to Diego.
Thank you, Elina. So thank you also for being part of the organization of this with Mirna, Florencia, and all the other people involved. So brief message from me before starting with the technical talks. Well, for the people that do not know yet, we are part of a big organization, the European Association of Geoscientists and Engineers, and I'm the chairman of the local chapter in the Netherlands. There are a lot of local chapters worldwide, but we are mostly collaborating with the local chapter in London, Paris, Oslo, Aberdeen, and now also Germany, that was established recently. And we are proposing this type of events. Luckily, we could go back to present live. So from September, we came back to have these live events. Before it was virtual. And we are keeping trying to do that until it's possible. So already this event and next event in the Tares will be live, and then we'll see what's happening in the program. We are also collaborating with the students. So we have here a lot of students from DOGS, which is the EAGE Local Chapter for the students in the Netherlands. But we are also collaborating with the Oslo Society of Exploration Geophysicists and other local chapter, also student local chapter in Aachen and so on. If you are interested to follow us, we have all LinkedIn page that you can reach, but you can reach us also through these emails. Our one is eaglcnetherlands@gmail.com. Elena is answering to that email, just in case you wonder. And we are looking for new members, for people helping out, also organizing this type of events in the board and so on. So this is the board for 2022. Apart from me as a chairman, we have Rita Strick as vice president. Elina is covering secretary and treasurer. Evers Loeb is membership officer. Maike Blau, event manager. Don Zanger, event assistant. Yuri, that by the way is coming back from Switzerland, so he will be more active in the future of the local chapter. Is the media officer and YP coordinator, and he established recently a website that I will talk about in a few minutes, where we have all our activities, the calendar, a lot of things so that you can check. Florencia, that is helping with the president, but also coordination with the Women in Geoscience and Engineer, and then John No as a student coordinator. As I mentioned, we have a brand new website, eagelcnetherlands.org. You can see there the board member, our activities, past activities, but also future activities. And we have also a link to a calendar that is coming directly to your Google calendar. So even if you don't want to check your email so often or go to the website, if you register and subscribe for that calendar, it will pop up immediately also for future event in your Google Calendar, which is quite nice. It's a new feature from Yuri. And now I will go to today's agenda. We had a nice welcome drink and snack, and after my introduction, we will have Innovation at Fugro by Dr. Rik Wemmenhove. I hope to pronounce it correctly, from Fugro Innovation and Technology. And then another technical talk on near-surface characterization for offshore wind farms by Dr. Johannes Singer, also Fugro Innovation and Technology. And then we leave the rest for a Q&A and discussion. I was told that around 7:30 we should start leaving the building because they have an internal policy after 8 p.m. nobody can stay inside. So I will ask you gently to leave at that time. Okay, so let me introduce the first speaker. I don't know what happened. Rik Wemmenhove, probably the second picture, I guess. Rik Wemmenhove is working as a technology in Fugro's innovation department. In this role, he's involved in various technical projects in the marine domain, with a particular focus on geodata acquisition, vehicle motion, digital simulation, and hydrodynamics. Rik has been working in the offshore industry for nearly 15 years. He received an MSc degree in mechanical engineering and civil engineering from University of Twente, and holds a PhD degree in applied mathematics from University of Groningen. So please, Rik, I will give you the stage for your presentation.
Okay. Yes, and thank you all for attending this session tonight. Very nice to see so many faces here. And, welcome at Fugro. So during my 30-minute talk today, I would like to present you a bit more on innovation at Fugro. What are we doing here? What kind of people are working here? What kind of projects are we working on? And the history of Fugro is quite long already. It's the company was founded 60 years ago in 1962. So we had some 60-year celebration just a couple of months ago. And in the beginning, Fugro was really, or it is still a geodata company, and it all started with something called CPT, cone penetrometer measurements. This was initially done just in the fields, here in the neighborhoods. And just a couple of years later, the company was growing back in the 60s, and we had some first offshore CPT measurements done in the end of the 1960s. So that was the period of time when the offshore industry in the North Sea area was really booming. First oil platforms were coming there, and there was a need for installation of offshore structures with CPT measurements. So this was really something that Fugro jumped into already back then. Nowadays we are nearly 60 years later, and just one highlight of last year is the vessel that you see here, which is the first uncrewed vessel inspection in the North Sea area. It was run from the port of Rotterdam with a vessel here and remote operated vehicle there. I will tell you some more about that later on in the presentation. So Fugro as a company is doing many different things. In the end, we're delivering a set of geodata to customers, quite many different groups of customers. It can be onshore, offshore, and it's not just, it's a data package we're delivering in the end, but there are different areas where we are focusing on as a company. It's the mobile autonomous robots and sensors, so the vehicles, the vessels, the tools that we're using to acquire data. But it doesn't stop there. It's we continue with remote operations and support services, basically collecting all this data from the field and get them as quick as possible into our systems in kind of real time. That goes into many digital analytics and cloud services, and in the end, the data is collected in a report and data sets that are delivered to customers. So those are 4 stages of the typical geodata projects. So it's onshore and offshore. Offshore, you see here a couple of examples of groups of work we're doing, like offshore wind development, deep water site investigations, remote inspections of existing offshore infrastructure. So this is offshore site characterization. That is what we call the early stages of offshore development. So that's really about mapping seabed and all its features before new infrastructure is developed. And then once a platform or a pipeline or a wind turbine has been installed, constructed, then after that there's a phase of operational phase, and then we're also really into the marine asset integrity. So that's monitoring the condition of this equipment. So we're doing many different things operationally and technology-wise, and this really deserves a decent innovation organization. So at Fugro nowadays we have over 400 people working in innovation. It's not only here, we have innovation centers quite nicely spread around the world. So you can see here in Netherlands and Norway, but also we're quite heavily based in the US and in Australia as well. Of these 400 people, close to 200 people are based in this tech center in Nodorp. So this building was built in 2014, I think. You can see it here. Here we are with close to 200 people. We have office facilities. We have workshops that we can utilize to put together equipment, do some testing. We have areas with screens for monitoring of operational work, and here you can see some photos of a recent team building exercise where we got some constructive assignments that required a lot of teamwork from all of us. So what kind of work are we doing here in innovation? So it's close to 200 people here in the building. So not just one team, but it's split up in quite a few small teams that are dedicated to particular topics. These are a few examples of these things. So it's on the hardware side, on the software side, quite a few design groups, but also embedded software, robotics, on the seismic side as well. We're quite interested. And now I have a number of slides to show you the kind of products, solutions that we have been working on in the innovation. Quite a few of these are already operational in the field, in the Netherlands or somewhere globally, somewhere elsewhere. And I would like to begin with something on geotechnics, because that's where it's all started with Fugro, as I said, in the 1960s. So this is a cone. So that's this cone you're pushing in the ground quite deep to characterize the properties of the soil, sand, clay, silt. Measuring the resistance of pushing the cone into the ground, and that cone has been evolving more and more from onshore. It has been moved to offshore operations as well quite some time ago. And there on top, you see an example of offshore CPT operations. You don't really see the cone anymore because it's sitting somewhere inside there. This is the sea-calf system. It's quite a big frame, a few meter by a few meter. It's here on the deck of a vessel, but when it's put into operation, it is lowered through a moon pool in the vessel all the way to the seabed, and then the measurements at the location can start. So from there, the cone is pushed in the ground. That's not super easy so because it's pushing the cone down. You have to keep it straight, so there's inclination measurement, and you need equipment to push it into the ground with a constant speed. So during the years, we have developed this sea-calf system with a metal with a coil, which is basically a metal structure that is coiled up, but when you push it down, it goes straight down. We have wheels with friction to put it down to the seabed. And these frames are quite heavy. They are like 10, 20 tons. And that's necessary to have enough force, enough static force to push this gun really deep into the ground. But there are some limits. I mean, if you at some depth, it's you can keep on pushing, but you don't get any deeper. So we are working on innovations to optimize that as much as possible, to get the gun to have good measurements, also at greater depth, because that's what clients are typically after. Have a good insight for wind turbine installation or other installation projects from 0 meters to 10, 20, 30, maybe even deeper meters below the seabed. You're getting these kind of plots and curves out of it. But sometimes it's not possible anymore to do these CPT measurements, and then you have to go into drilling. So Fugro also has a number of drilling vessels in use, like the one here. So then you're drilling out in the borehole before you can do CPT measurements at greater depth. The boat over there, it shows one of our colleagues doing a test next to the building here. It's not that one was not to prepare for some rig construction or so, but it was a trial of a seismic CPT. So there is some seismic vibrator there. It's a CPT measurement in the track downwards. So this was a test to qualify this system. Also on the one more slide on the geotechnical topic is the deep drive. Also here on the image you see a coil on top of this vehicle. It's a moving vehicle on tracks that can move around on the parking lot here, but it can also move around somewhere in the field. And it is a remotely controlled vehicle, so there's no driver or so on board necessarily. The driver can be a few hundred meters away from it. And the nice feature of this vehicle is that you can send it on a small mission to a hazardous location, do a CPT there, and then come back for the next measurement location. So also here we are using basically transferring technology from offshore to onshore. Sometimes we also do the other way around. And going back into the marine domain, maybe some of you have seen it in the news. I think it was last year in November when first USV was launched by Fugro in commercial operation in the North Sea area from Port of Rotterdam. Was the one over there, the Blue Essence. But we have a couple of different types of uncrewed surface vessels in operation and under construction as well. The reason we are working on these USVs is that we really see it as a step forward from conventional survey vessels, which are bigger, larger crew, burn more fuel. These vessels, they don't need anyone on board on the vessel. They're much smaller, so you need less fuel to run an operation, and it also brings efficiency and benefits for us. And at the moment, we have a couple of these Blue Shadow vessels in operation, and they are tailored for high-speed hydrography. So that's really mapping the seafloor, big areas, multi-beam operations. Also working, so those already exist there and are in use. We are also working on the next generation of this type of vessel, which is called the Blue Prism. That one also will have towed cables with sensors. And that's mostly for survey operations, for site characterization. And then earlier on I talked about site characterization, asset integrity. So asset integrity, that's about monitoring of pipelines and cables, other structures. That's where these vessels come into play. So the Blue Essence, the one on the left there, it's only 12 meters, but still a decent vessel. That's a very special vessel because it's not just a vessel, but it's also a mothership for a small, for an ROV, remotely operated vehicle. You can see there, which can move over the object that you want to inspect, for example, a pipeline. So this ROV is the blue Volta. I will show some more photos of that later on in this presentation. I think on the next slide. And the one there, the blue Eclipse, will be next. It will be the bigger brother of the Blue Essence, a bit more size and a bigger underwater vehicle as well. So which enables us to do more types of work. So remember those ROVs, they come back here on this slide. So here you see a photo of the Blue Essence from a drone, I think, with the ROV being pulled on board here. You see a lot of foam and turbulence. That's because the thrusters are working hard to have a smooth recovery into the payload bay. So this vessel has an open transom in the aft. And the main function of this open transom is that the ROV can be pulled in such that it's working on site near the seabed. But when you have to go back to port in transit, then your ROV is safely on board the vessel, and you can sail back to port as one vehicle. And this vehicle, the ROV, is has been developed fully in-house here at Fugro. So we have underwater robotics team here in Noordorp. We're spending a fair amount of time on that. We have some test facilities as well here in the house. So this photo there is the ROV test tank, which is just 20 meters away from here. So that's basically a big, small swimming pool that can be used for trialing the software testing and testing the thrusters and testing the movements and steering algorithms of the ROV. Very nice. And then if that's all functioning well, then next stage before the ROV there is to do some trialing on a not at sea, but in a sheltered environment. Like my colleague Richard, he is doing a test here. He has a big pole in his hand to keep. He's trying to push away the ROV, and the thrusters are working hard. The algorithms are working hard to keep this particular position here. So I think it was working here. So after that, he was one step further in improving this ROV. And the image there in the top right shows the Blue Volta ROV. So it has cameras and accelerometers and functionality on board. Another product is the vision technology. So we have a dedicated team. We're focusing on the smart cameras, and this technology is used a lot as well for asset integrity projects in particular. So they have a couple of different products. Two of them are on the slide here. There's the quick vision technology. So it's a combination of cameras and software. And so you have augmented reality feature. And this AR system, it's basically putting lines and detecting the boundaries and the edges of underwater structures. For example, here you can see a mooring line, and then based on the computer on the video footage, there's a protractor tool which automatically detects finds the right angle of this mooring chain, and this is done in real time. So it's a very impressive feature of this system. There's also a tracking alternative, which is convenient for installation of wind turbines or offshore structures. So then there's a target pre-installed on the construction, black and white pattern, which is used to track the X, Y, Z position of that particular target. Next to the quick vision, the vision team also has in ClimaCam. In ClimaCam, it's also a smart camera, which is used in particular for installation work of monopiles. It's one important application. So for these monopile installations, it's very critical that the pile is put straight into the ground with a zero angle. The tolerance is there really tight. You cannot have like a few degrees off, so it must be it's really decimals of degree. That's what I understood. And we're using the ClimaCam technology to monitor this. So here, the ClimaCam, I think it's installed on the moving vessel. So there's motion compensation in the camera system integrated to make sure that it's a correction for that, such that it's possible to have a line in the software next to the structure to make sure that the angle is about 0 degrees and not out of spec. That's some seismic. Seismic is probably something many of you are familiar with. Passive seismic is seismic without a strong sound source. So I had some more images here, but it's just this photo, which is right. So here, this is an example of a job where the receiver sensors were buried in the ground with data loggers here. And the purpose of this was to measure shear wave velocities in that area ahead of the construction of infrastructure. So there were some nice 3D plots with many data points for this particular area created. I think Johannes will tell more about this passive seismic technology. Oh, there we are. So the image there on the top left, that's the shear wave velocity with data points from the underwater files. We're also still doing marine seismic, and the application is mostly offshore wind these days. For the installation of offshore wind farms, it is really critical to detect boulders in the subsurface, other features. Before these monopiles are installed, the operators need to make sure that there's nothing there in the seabed that can stop them from bringing these monopiles down. So a boulder of 0.5 meter or 1 meter, is something that is stopping this piling operation. And then the question to Fugro typically is, could you characterize the seabed to quite a decent depth, as deep as the monopiles go, and indicate us where the boulders are. And to do that, we use 2D or also many occasions 3D ultra high resolution seismic. So this resolution of 0.5 meter or 1 meter, that's quite demanding. At the same time, we don't have to go super deep, only as deep as the monopiles will go. Consequence is that we have short streamers, but with the dense spacing of the hydrophones. So this is a photo of one of our vessels. I think this was the Fugro Pioneer with a 4-streamer setup and 2 sources. And this is a 3D image of the underground of the seismic system that we are offering and operating. I think the last topic I'm showing in my presentation is on UXO, unexploded ordnance. That's really a problem in the North Sea and the Baltic Sea area, because in the 1940s there has been a lot of ammunition which has been dumped at sea. Back then people thought it was not an issue, but now we really encounter these as issues because it's really a booming installation of wind farms, pipelines, cables, the types of offshore infrastructure. So before doing all that installation work, you need to make sure that the seabed is clean at the surface, but also 1 meter, 2 meters into the surface and deeper as well. So I've got some work on UXO detection first. So this is the Fugro GeoWing. It's a system that we developed a number of years ago. It's here it's still in the waterline, but when it's in action and operation, it's out. It's behind the vessel, just a few meters above the seabed. So this is a steerable wing, which controls the vertical position, a few meters above the seabed, and also the lateral position. And then attached to the beam is quite a decent frame with magnetometers. There are 5 of them. And they are used to, but those magnetometers, they are recording continuously and tracking magnetic anomalies. And in the end, you get a map of the seabed with different colors to indicate where there's a metal feature in the ground. It can be indeed UXO, it can also be a bridge or a bicycle, but something else. Yeah, so that's about detection. Then there's also, if you detect a UXO feature, which may be an unexploded bomb from the Second World War, then well, you can either get afraid and stay away from that area, but that's not always possible. So yeah, sometimes there's a need to remove it, take it away. And as a tool for that removal of UXO, we have quite recently developed a sea out system. As you can see here, so it's a big river that's mobilized in this case on a jack-up platform, shallow water. Operators from Fugro here, and this tool it's about it's first dredging around the UXO and then securing the area and taking it out. I think the sea out was recently used on a cable landing in North Holland earlier this year. Let's see. That was my last slide. I have one more on questions. Do we have time for a few questions, or?
Do you change the cone diameter?
Yeah, we have a few different types of different diameter. Yeah, but it's not something we are changing all the time during the job.
Because can't you get all the information also from a small diameter, which is easier to penetrate?
Yeah, but it's not only the point of the cone; it's also there's a sleeve and a long rod above it. So it's as far as I know, it's a bit depending on the type of soil, which well, the area where you are. So there was some pre-study desktop work beforehand. Then a choice for a particular cone.
Your technical engineers have strict rules about the diameters of the cones. It's more a question of compliance.
I had a question on the blue prism system. You mentioned that had that towed cable. I wasn't sure what those cables were for and how long they were. And if you have a problem with an autonomous system, how you keep other vessels away from those cables.
Yeah, that's a good and fair question. It's well, we are planning to use those for example, for sonar operations, and they'll be underwater. But at the same time, it's similar to what we are already doing with regular crewed vessels, because they're doing similar operations with similar cables and sonars. So it's but they're deep underwater. They are those cables will be. Well, closer to the seabed than close to the sea surface, so there's no need for a buoy or a beacon at the bottom. There's a question there in the back.
Can you say something more about the measurements that you're making with ROVs? So what type of measurements are you making?
A lot of visual measurement, like camera footage. It's typical. Also, yeah, there's also some option for CP measurements corrosion features, corrosion protection, that's place.
You mentioned it also had example. So
Yeah. So we have full control of the orientation of the OV.
to add to that, let's have if you operate control reservoir on that reservoir is that you start to use it for tearing, cooking. The next level of, let's say, the whole rail of operation is when during manipulation, which is a lot of magnitude more complex. Think about the operator being out of the way and trying to fiddle on the little panel floor, or I think on anything like that. So that's the next step in the approaching, which works with the inspection on the manipulation system, but in general, it all reads the new intervention function work for where you are really considering data in side of the mainland. And so is our visual inspection investment and not really something. Your question of the Excel, they are usually found in board virtual application systems or for limiting entity. They could carry like a preference of those information. And I hope they will come.
Small vessels, uncrewed vessels, are relatively small, which is good for fuel economy, but you're becoming more sensitive to inclement weather the smaller you are. Does that mean that these vessels have to operate close to shore, close to a port?
Not necessarily. It's of course, yeah. A shorter vessel with less length, it will always be more susceptible to weather. But it's something we also take into account during the vessel that designed to really focus on vessel stability, so we can maximize the number of operational days per year. Also, in the North Sea area here, which is quite demanding.
Well, again, if I make a comment here, actually, the bit counterintuitive. The small vessel does the opposite of what you would think, and operate it in much more difficult conditions because it's built in a way that it can almost roll over in any direction. It can literally pierce through the waves and so on. So it's meant to operate to all the extent the operational window. Where you really don't want to have a crew on a manned vessel that will waves are 10 meters high. We have some famous footage from the Southern Indian Ocean when a 58-meter vessel, where you see the most here, goes on 15-meter waves. I mean, you really don't want to be on that any something. But if you scale it down and think about that 12-meter vessel that can actually go in enormously bad sea state, it simply will roll and swing around, but it doesn't really.
If there are other questions, we have a Q&A session at the end, so we can have more. But for now, a round of applause for Rik. Maybe we can take 5-10 minutes break so we can have another drink, a little bit of food before starting with the second presentation. So let me introduce the second speaker. Johannes Singer has been in Fugro since 2010, initially being part of the geoscience division and later of the subsea division. He also managed the Fugro branches in St. Petersburg and Dublin. Johannes is currently working as a chief scientist. He holds a PhD degree in theoretical physics on quantum Monte Carlo simulations for a high temperature superconductivity. He later worked both in academia and in industry. His interests span the fields of geoscience, geotech, autonomous vessels and robotics, asset monitoring techniques, among others. So thank you also, Johannes. I will skip this presentation. Here we go.
Very much. I'd like to emphasize my origins in superconductivity because that's another Dutch invention about 100 years ago in Leiden. Commonly honest was experimenting around and trying to reach the deepest possible temperatures, and in that context blew up his lab 3 times and discovered superconductivity as a side effect and got the Nobel Prize for it. So before I even know that I would have to end my life in geoscience, geotechnics, and in the Netherlands, I was working on a topic which was invented by a I'm trying to tell you a little bit differently to what Rik nicely did. He told you about what we invent and what we build and all the big things we create. And I took the opportunity to maybe talk a little bit about an aspiration which we have. How can we improve the field of geotechnics by going from real digging and poking to something which I would like to call virtual geotechnics, or I know my colleagues who are real geophysicists hate the word geotechnical imaging, but hey, I'm not a geophysicist, but I'll never become one, and I'll still talk about it. So the idea is, how can we image structure and properties of the near surface for building, construction, monitoring, and I'll tell you about a few weird ideas and connections, and maybe some of you find it interesting, maybe. We already have been pestering our friends in Delft and in Delphi on the subject, so let's see. So to start with 2 things which everybody knows. First of all, seismic is a deep targets for resource exploration and monitoring, and near surface is a rather problem than a target. Well, before I joined Fugro, I worked for Shell with people like Yelp, and I remember the time when things were called statics, near surface noise, and well, literally that's the sound we are living on. And the second thing is, what is geotechnics actually? I guess geotechnics was invented when people started to build cathedrals and realized for the first time that they fall down and started to dig what happened to find out what happened. So it's about the investigation of the near surface and its properties which are relevant for building and construction. So where can I build a foundation? How deep do I need to make the foundation? Do I need to improve on it? Do I need to pile and so on? And that is usually done by digging, poking, drilling. Well, that's how we started out. You have learned about cone penetration system, and that's another thing where I would say the typical Dutch invention, because I'm coming from the mountains where people build houses on granite and rock and consider everything which is slightly less stable than that as not worthwhile to build. Then when you come here, people consider sand as a good ground and mud as a thing to avoid. So the fact that a company like Fugro invented 6 years ago the cone penetration test is not surprising, because it was literally meant to poke into the ground and see where there is a solid layer and how deep do I have to go to support my foundation. But in other words, if you compare that with the medical industry, the I started to do that because I had some surgery myself, and I'm happy that I don't live in the 19th century, because there I would have looked up posteriori what happened. That's how geotechnics also used to work. Building breaks down, people look up, what happened? But in the 20th century, they started to do the poking, the minimal invasive investigation, cut little holes and look inside, a bit like the CPT. And these days, when you have an issue, you first start to image the body. And that's actually quite an amazing process if you look at it closer. It's amazing for very many reasons, because it gives you the structure, it gives you the distribution of things, it gives you certain physical properties. And you see that right online. I mean, it's not like seismic processing. Well, we do an X-ray and you get your result in 6 months. It's right next on the screen. And hey, you can really annoy your doctor when you turn around and say, well, I would do that differently. So you've seen the poking thingy, that's where Fugro started, and that's where geotechnics really mostly is these days. And if you want to do it offshore, you can also do it, just get bigger, more complex and on, but it's still poking with the same type of thingy. And now you look at the medical industry, and you see X-rays and sonograms. I mean, X-rays like that exist in more than 100 years. Röntgen got the first Nobel Prize in the early 20th century by seeing his own hand and his ring under X-rays, unknown rays at that time. And you can see your own kidney life working in your body. And again, I mean, it's not a hi-fi picture, it's not wonderful, it's not whatever, but it's right next to you when the guy the investigation. And you can go a step further and you can't just see what's the structure if you can also determine properties. I mean, can measure stiffness, solidity, things like that, whatever the medical guys call it. There are techniques like shear wave elasticity imaging, which are quite amazing because they give you literally the equivalent of geotechnical properties in your body. And the setup is not very complicated. I mean, it's one head with a steerable array in it, which can be source and receiver at the same time, just moving over. And the shear waves are actually quite low in frequency. Hundreds of hertz, not megahertz, kilohertz. And as I said, yeah, cool. They made a guy to look at the other side, but whenever you get something like that, make sure you see it yourself in the screen. It's online. So the question now is, can we do the same for geotechnical parameters? Can we non-invasively look at the subsurface and determine the structure? Of course, we can do that. We all are geoscientists, but can we also measure properties which are relevant? And yes, we can. I mean, Rik has been pointing to passive seismic. Passive seismic is particularly interesting because it tries to utilize surface waves, interface waves, which have lots of shear components. And obviously, if you measure shear components, you measure the stability of the rock matrix instead of the compressibility. And if you do that in 3 directions, get essentially a cube of information which tells you everything about the subsurface. And it doesn't tell it just locally. You get a continuous three-dimensional shear wave velocity cube, which tells you everything you want to know about the new surface. And you also want to do that for the offshore case, of course. If you plant such a wind farm tower into the subsurface, you want to know what's in the new surface, you want to know whether there are boulders in it, but you also want to know what's the stiffness. You want to know whether your tower is sustaining in 10 years after enormous wind cycles, loads, and waves. So that becomes in one direction a question of simple imaging. And here, for you guys coming at least partially from the oil and gas industry, I thought it would be instructive to see where we're going. Go from normal high resolution, ultra high resolution to God knows what centimeter type of resolution. That obviously gives you all the hopefully pictures which pay off and give you in the near surface in the first 20, 50, 100 meters the necessary resolution. And show you features which might tend to you see a high resolution and an ultra high resolution picture of the same area. And you can drive that even further. Obviously, it gets more complicated. No doubt, if you send a kilohertz down and you have short wavelengths, positioning, and your streamer, well, yeah, it becomes shorter, but it also becomes more difficult to operate. It becomes a challenge in itself. And as Rik pointed out, the boulders, the famous boulders, you can drive it as far as actually seeing them in your seismic images. It's quite interesting if you try to do that. Being a conventional physicist by heart, it's somewhere between I don't know, Rayleigh backscattering experiment and the Millikan experiment for those of you who have ever done physical practica, where you detect things which are smaller than your wavelength simply by scattering and creating a hollow, and so it becomes quite interesting from structural point of view. And obviously, it becomes also interesting from a property point of view. As I said, if you try to map shear wave velocities, you can create your cube of shear technical properties, and then you can merge it one way or the other to actually get the geotechnical image of the subsurface. The downside still is, hey, you see all the sensor locations, and it takes still how long we're not, 2 weeks, 3 weeks, 5 days to process. So by now the patient might be dead. But, well, there's still let's say, a challenge to go. Yeah, here's another picture, which, by the way, I took from the amazing PhD thesis of Hoyce, who I think was somewhere here. So, I don't know. Let's have a chat. Is it too good to be true? What's that revision? Obviously, there are certain things which we can do, and there are obviously certain things which we can't do. An MRI of the subsurface is quite difficult. I mean, the physical signal is difficult, and the fact that we don't usually have the ability to rotate around our body is difficult. But we can acquire PNS waves, we can acquire surface waves, we can play with active and passive sources.
Obviously, passive sources aren't sourceless signals. They just are natural source signals. It's the biggest source you can have. The earth itself, and the wind and the rain, and God knows what noise. As I said, particularly interesting because waves which move on the surface on an interface have a large shear component, both on the land side as well as on marine side. The disadvantage is they're low frequent. So you can do a high resolution image with 1 hertz. That might be good. The complexity of the acquisition, you're still deploying hundreds of sensors or even thousands of sensors, which isn't really the picture of the medical imaging which you have seen before. So the complexity of acquisition was a guy just pulling his head over your body and at least see basically what's going on. Is it a boy or is it a girl? At least that's what he was asking me when he's on my belly. Topography is obviously an issue which is much more of an issue if you work in the first 20, 50 meters than it is in deep seismic. Yes, again, with the joke about statics, people usually try to get rid of most of the topography and most of the neosurfacing. We can't neglect it because it's all we're living from. Acquisition in populated areas and cities. The target of itself, can we apply sources? What sources can we apply? How do we do that? To not shake the building stand, which we want to sustain. Can we use passive signals? Can we use quiet active signals? Environmental impact. Well, you think whales get crazy in the exploration band, 3 to 120 hertz in deep water. Hey, they really don't like a kilohertz in 25 meters of water. So it becomes an even more complex topic to have an environmentally sustainable solution. Where do we acquire? Can we, if we do offshore geomedical technique, can we do that also in mid-water with a streamer, or do we need to go to the seafloor? What is the positioning requirement and so on? Imaging inversion. Well, our friends from Delphi have already encountered our painful discussions on. No, that was not a seismic survey. Our painful discussions on.
You're right underneath.
Oh, I'm right underneath the speaker. Should have known. Is it feasible to do 2D or do we need 3D? And what does it mean if we need 3D? I was talking about the fact that we want 10 centimeters, half a meter resolution. How many lines is that when you have a wind farm of 100 by 100 kilometers? Is that technically economically feasible? What is a reasonable resolution? Is it what the CPT shows? The geotechnical community now gets a CPT which has centimeter resolution. Do we really need to know on a 20-meter monopile centimeter resolution, and what is it? By the way, you have to, under your question, there is no physical law for the size of CPTs. It's just engineering intuition.
I was told so, yes.
Speed of acquisition, can we ever go to real time? I mean, literally that's what our clients are asking. The building company, which is building a new shopping center in the middle of Paris, they want the information and the backer is behind you. So they don't want even 5 days of acquisition and 5 days of interpretation. They want literally some medical thing going through here, something, problem, take care of it. And how do we sell seismic to construction industry? And don't take me wrong, I'm still a scientist. I'm not asking about monetary selling, but how do we start to speak the same language between the building engineer and the geotechnical engineer and the geophysicist? If I show him a nice wave cube, what is he going to do with it? And do I need to convert it to CPTs? Lots of people talk about creating virtual CPTs out of shear wave cubes. Yeah, well, you can do that because the building engineer has now understood what the CPT is. Does it really make sense to create some kind of funny poking tool data out of a shear wave cube? Obviously, no, why would you do that? But how do we communicate? This maybe is also something to throw back to the EAGE, connect more to the building industry. The building industry is the future. Much as I hate it, but it is. And building offshore and building into shallow water, energy transition infrastructure, wind farms, energy islands, cables, pipelines, but also cities. Right. Cities, I mean, Jakarta, places like that, they are literally offshore projects or transition zone projects. So the building into that area becomes the challenge of this and the next century. And it's an opening for geophysics, an opening for geoscience to help. So, medical geotechnics it is, right? Thanks for listening to me. I know you long enough.
Well, the question I have is, many of the measurements you do, you measure actually elastic or parameters of the subsurface. Now, you want to have actually the rock properties. So do you use a rock physics model to transform your measurements into rock properties?
Well, that's ultimately what we try to do, to transfer things into, let's call it soil and rock properties. But you can't do that without ground truth. I mean, a shear wave cube doesn't, let's say, one-to-one and without ambiguity transform into a rock property system. So you need to have ground truth somewhere. That's the bad side. The good side is, well, the near surface of most of the rest of the Netherlands is the same. It's just a question of where is the good zone and where's the bad zone. So it's not a fast varying situation. So you can get away with a little bit of borehole information, maybe an outcrop or whatever. It's just conventional geological work or conventional petrophysical work to augment that. But the same is true for the medical industry. I mean, Röntgen's picture only shows you bones because we know that by now. When he first saw it, was also surprised what he sees. And it's not that could have been water pipes. Thanks. Any further questions? Cool.
If you were to sort of like categorize or prioritize it, say like your top three priorities in terms of value and the needs for Fugro, what would you pick? How would you prioritize the first three?
I think they're more or less prioritized. The first thing we have been attacking, can we acquire ENS and active investment in surface waves? Yes, we have shown we can. And academia also has shown, I mean, I can get a barometry with shear waves. Doable. The complexity of acquisition is the next biggest thing to avoid thousands of sensors and weeks and months of acquisition for a building project. The building industry has, compared to the oil and gas industry, a very simple rescaling factor. Everything has to be at least 10 times cheaper and 10 times faster. Topography, acquisition of populated cities, I mean, you can change a little bit, but I guess it's was reasonably flowing out of my mind in terms of complexity. Yeah.
Yeah, I also don't need to ask a long topic, but on the topic of speed of acquisition, is it just about impatient customers, or is there any scales that we can create that we have real-time responses on this?
Well, I mean, as I said, if you're in the middle of the desert, it's probably just an impatient customer. If you're in the middle of Paris and you have to block 6 main roads, and then it's not an impatient customer, it's a necessity that you want to not impede things any longer than absolutely necessary. So a little bit same with medical patients. I mean, if I get my annual checkup, yeah, it can be in January, it can be in June. If I'm sick, then I want it please now.
There's no creative use case because we have a new response we can directly react to what we see.
Well, without going too deep into what we are trying to do, obviously we're trying to stagger it a little bit with, can we find quick scanning approaches where you can see at least something is going wrong in the subsurface, and then do a closer investigation. Do I always need 3D cube? Maybe not. Sometimes a 1D or 2D thing might be good enough. But in a lot of cases, yes, speed is an integral part and unavoidable.
So what are we learning from the medical industry? I appreciate that MRI scanning or X-ray tomography is a different problem from the seismic problem, but are we really getting insight into what we could be doing differently in the seismic industry to improve that turnaround time?
I can't give you an answer. I guess I would consider myself as being inspired by the medical industry, and I'm torturing a mean to see if we can learn something from it. I don't know yet whether we can learn something from it, but I think probably we can. I mean, the design of their system is really simple and pragmatic. Instead of having all those complex setups, I have the array head, which can do both. For example, you could think about building something like that to scale that. You could think about building some of the algorithms also, which are not geared towards ultimate fidelity and image quality, but just to see whatever you need to see. So somewhere between being inspired and trying to understand what we can learn. Come back in 5 years, then I'll be about to retire, and I can tell you what I've learned so much.
But yes, it's a surprise to me because, of course, you can argue it says, I know, an MRI scanning results or what have you, they have been so much faster than us for a long, long time. I'm not understanding the fundamental mathematics about why they can do their processing so much faster than we do, when it's just the number of pixels in their image compared with what we have or have you.
Well, it's partially the pixels in the image, but it's also partially the algorithms which they use. I mean, where we start to argue in very complex inversions and how much detail do we need to see in seeing the inversion. The guy just wants to know it's a kidney, and he expects when he puts his head here that he probably is a kidney in the brain, so his algorithm can adapt to that. And he also knows that everybody is built up the same way. I mean, a bit more and a bit less fat, but hey, it's always the same thing, skin fat, whatever. So we can learn from that by pragmatically building up algorithms which are not trying to squeeze the last bit out, but just see whatever needs to be seen. The cables, the cavity, the cavern, curves, also sinks maybe. Pragmatic, and hey, if I would be able to use NMR instead of acoustics, I wouldn't be talking about seismic. It's so much more interesting.
That was going to be my question. As Jaap said, you're looking at the moment. You're looking at elastic properties using acoustic sensing. But if you thought about combining it with electromagnetic or other gravity potential field methods,
Yeah, I have. I hate it. If you think seismic is visible, then I can tell you, which I said a chat with Everett before that meeting. Diffusive signals are a pain in the rear. Yeah, you can use GPR and you can use conductivity, but the scales we are looking at and the types of soils we are dealing with, in particular, again, in the Netherlands, I wish they would be home in Bavaria where everything is high resistivity and EM goes to the center of the earth, but you're in a conductive environment. EM is, it's literally. So, yeah, obviously multi-physics. I have been at home. If you don't know what to do with seismic, you scream for multi-physics. I think there is a lot still to be found in, let's say, elastic and acoustic and seismic style of signals, which we haven't explored yet. And if you want to go to gravity, hey, the gravity anomaly of a 4-meter long wooden pile in Amsterdam is limited.
now in terms of, for example, as you said, real-time acquisition, CSEM is contactless, as you sail along.
Who told you that? I doubt that.
These problems is about finding out if things take, not so much getting super good for years.
Yeah.
Which I'm really amazed at the offshore high resolution seismic, 3D seismic, that's really spectacular, but it's very unlikely that whatever happened planned. But most in the subsetup case, you just want to know things change. So, I mean, since you're programming all these models anyway, how do you just equip them with like 100 sensors per hole, cemented, just report if something changes?
Or fibers or other things.
Or fibers.
Changing it is an interesting aspect, in particular if you look about critical structures like dikes, levees, dams, and on, which you can also treat that way, and you don't want to see where the dike is, because you can see the body thing in front of you. But you want to see how liquid saturation changes, how ability changes, and on. So changes are, at the end of the day, things which we want to see, but we still don't know enough about the near surface of our building area to just rely on changes.
But it's like I don't know, right? But I usually drive shitty old cars, which come with a subset of sounds and noises, which are always there, which are I'm okay with. But as soon as there's a new sound, I know something changed. And maybe that's the same way. Maybe we don't need to understand the entire system. We just have to be on alert. There's a new sound.
Yeah, but this is another interesting topic which I would consider amongst my areas of interest, just monitoring, and you can see how things change. And that's an even more unresolved thing. If you have a building in the subsurface, people consider monitoring at the moment to look at the building itself, but forget about the fact that it sits in the subsurface. And the fact that the bridge starts to develop cracks usually comes from the fact that it moves in the subsurface. It's not necessarily that only that the concrete is shit. In summer it dries out, in winter it swells on, the thing moves, floats, does all kinds of things. And the foundation area and the area around buildings is really a very difficult one because we can't poke into buildings. So the non-invasive acoustic approach to see the foundations and change the foundations and how things have compacted after we drive piles into the ground and past the soil improvement which was expected by 500 piles really happened. All those questions. Yeah, well, I guess I can't retire in 5 years. Oh, but yes, in principle, changes to quite a degree also absolutely commission. And maybe not really that high resolution thing. Hey, I mean, I showed you that because I want to show mine is lower than yours. Or my resolution is higher than yours. But maybe it's not necessarily what is needed for this own decision. For finding boulders, yes, it is. But maybe we can do that differently, as I said, mitigation effect.
Do you know what the requirements are on the regulatory landscape for all these, for let's say offshore storage of hydrogen and CO2? What do governments expect or want?
To be honest, I don't know. I wonder myself about that. Monitoring is a critical thing. I'll tell you a German story because I can't tell you a Dutch Rijkswaterstaat story. A couple of years ago, I went to the Bundesanstalt für Autobahnbau close to Cologne. Generally, everything is an Anstalt, as you know. And I talked to them, well, wouldn't it be cool to start monitoring bridges? And the guy looked at me and like, why are you boring me? In Europe, bridges don't break down. That was 3 weeks before the bridge in Genoa broke down, and I thought I should send a quote from him to the newspaper. To be honest, I don't know. The regulations for monitoring, and forgive me my joke which I made before, but the regulations are relatively old-fashioned, mostly visual inspection. So every year somebody goes to a bridge, to a windmill, has a look. Oh, nothing happened. Good, fine. Let's go home. And next year it comes again. So this is a responsive thingy. It's not a predictive type of maintenance. Nobody really investigates. Something is developing up, and it would be good to have an earlier look. And if we start to repair now, we don't need to tear down the whole bridge. We can just make a minimum repair, or the wind tower, or all those things. Nobody really does that. Or academia does it. We do that with Delft. We look into that. We do experiments on that, and we show our clients how cool that would be, and they say, really cool. And we say, okay, yeah, really cool. So, the point I'm trying to make with some somewhat disrespectful statements is infrastructure and the amount of money which is in infrastructure and the amount of cost which is in infrastructure is so huge that everybody tries to avoid to touch it. You think about the bridges of Amsterdam, 1500. If they would have to monitor each and every of them, Amsterdam would be spending money on bridge monitoring, but on nothing else. So they simply take a risk and say, okay, well, some of our bridges are 500 years old, they won't fall down next week. And that will not. Only happened in Italy.
In answer to your question on CCS, I mean, there's barely a country out there that has any standard things. It's up to you as a proposer of the CCS project to tell them what your monitoring plan will be. That doesn't even necessarily need to be fixed. I mean, in Canada, on one of our projects, they've monitored intensively to start with. And then they've seen that the carbon plumes are behaving pretty normally and as expected. So we don't do as much 4D monitoring there as we did before. But there's very few standards out there. But the regulatory authorities to approve what you put forward as a plan, rather than in most cases then proposing any minimum standards.
Yeah, I know. And carbon sequestration is the next level of craziness. And I've said this storing of nuclear waste. Because the timescales become so long that none of us really knows what the prediction is. I was talking once to a client about monitoring some nuclear storage thingy, and he was asking, and how long do you give warranty? And I said, well, how long do you need? And he said, 1,000 years. Those things are beyond my imagination. But even monitoring of buildings and infrastructure is something which where we should do something, because it would avoid things which become critical for us. And it's really not the breaking down of the bridge. The guy from Germany was actually, I have to admit, right. Because do we have 200,000 bridges in Europe and one broke down? Okay, fine. Bad luck. But what happens is that more and more bridges deteriorate, and critical infrastructure has to be shut down, because when the guy comes every year and has a look at it and says, okay, well, that thing here is not usable anymore, and that happens on two critical points of the same network. Think about, I don't know, the Harlingfleet Bridge and the Moerdijk Bridge going down at the same time for the next 3 years. Think about the traffic jams in the morning. Miserable. Think about the cost also. The government, the state, the nation has a budget every year to maintain things. They don't want all of a sudden 5 bridges have to be rebuilt because each of them costs $500 million. They want the smooth planning, so they need to know when can we do what, and when do we have to do what, and can we let that thing here rest for another 2 years or 3 years. And yeah, sorry, we got into a completely different topic of my speed.
Well, I'd like to make a remark on that. Actually, I followed the presentation by Equinor. And actually, what they do is they measure lots of things on a platform, and they have machine learning. And what they do, they sort of try to predict when a particular equipment part should be replaced, and not because of a schedule, every so many years it should be replaced, but based on the measurements they do, they can predict that, okay, I think it's safer to replace it now, so that we don't have to shut down the whole system. And I think in that area, there's a lot can be gained and a lot can be made possible. So I'm quite optimistic about that sort of preemptive sort of prediction of when things should be replaced.
Well, but it depends on who your client is. Yeah. I don't need to convince KLM that they should do predictive monitoring of their engines. They know by the time when the plane is landing that the turbine has an issue, because they continuously monitor it.
So there are possibilities.
But the Rijkswaterstaat doesn't know a lot about bridges. And that's not the despective statement, it is just what it is, because, as I said, it's also an overwhelmingly big task for a society. But if you don't have any further questions, thank you very much for the attention and listening to my bad joke.
very much. We covered already the Q&A, I guess. So let's go to the final remark. Well, first of all, I want to thank Rik and Johannes for their presentation. Maybe, Eileen, if you want, we can give a token of appreciation for your two presentations. Yeah, maybe if you can't hear, we can take a picture as well.
Thank you very much.
Thank you very much for the presentation.
So thank you for presenting. And then, of course, Fugro for sponsoring the event, for hosting here, in particular, the work from Eileen, Florencia, Mirna, and all of you for your participation. So I think we can close here the meeting and the event, and see you soon, next time in October. We will probably in the terrace watch the website for the news and updates. Thank you.